Okay, we'll wait just a couple more minutes. But while we're waiting, today we're just going to do one of the sections that I originally planned to do because, like I said, they scheduled a faculty meeting at 10. So I don't want to have to rush through something. So that means that schedule that I put out, I'm going to have to redo. I also, they kind of implied that we might have like a professional development day. I don't know if that's going to be next week or the week after, but that would be like a no contact day with students. So that would be like a day off for you guys. So I'll have to go back and build that into the schedule as well. And I think we're allowed to have up to 5 of those. So I don't know how many they're actually going to put into the calendar. I think we'll know more after we have that meeting today. So we'll just go through one section. It should be pretty quick. How's everybody doing with balancing redox stuff?
Pretty good.
Pretty good. Okay. And I did, I don't know if you saw, but I did post me working through the first 2 problems on that packet that you guys have. If you want to see more examples, I can work more of those out. But those are just, I think once you get the hang of it, some are harder than others. Like I think number 3 on that packet's probably a little more challenging than some of the other ones, but it shouldn't be too bad once you do a couple of them. Okay, my only issue here is I don't know what happens. I guess it tells me if somebody else is trying to get in, so we'll just close that out. Okay, so if you get a message from somebody, if somebody says they're waiting and I'm not letting them in, let me know. I think it's gonna pop up here and tell me. Can you guys see the slides on your computer screen?
Yeah.
Yes, good. Okay. All right. So let's look at voltaic and galvanic cells today. And like I said, we're just going to go through one section. So it's going to throw that whole schedule off. I'll make a new one. I'll post the new one for you. But that way we won't have to rush through this as much and it'll give you a little bit extra time today. So what a voltaic or a galvanic cell is, it's an electrochemical cell that uses a chemical reaction to generate electricity. So these 2 words, voltaic and galvanic, they mean the same thing. Some textbooks use voltaic, some use galvanic. This one tends to use voltaic a little more, but you'll see both of those. So we'll kind of try to use both of those interchangeably. The other type of cell that we'll talk about at the very end is something called an electrolytic cell, and that's kind of the opposite of what this voltaic and galvanic is. So there is another type, but we won't talk about that until the very end. So when you have one of these cells, what you're doing is you are causing the natural transfer of electrons that happens to certain chemicals happen over an external circuit. So when that happens, it's actually generating electricity. So if we look at the example here, these are both spontaneous redox reactions. So if I put copper, or I put a zinc strip into a copper solution, then the zinc ions are going to, the zinc ions are going to go into solution, and then those copper ions are going to deposit themselves on that piece of zinc. So there's actually a reaction, a redox reaction happening here. So the zinc is going from zinc metal to zinc +2. So what this is doing here is going from zinc metal, so zinc is a solid, to zinc +2. So this is losing electrons. So there's an oxidation reaction happening for the zinc here. And you can kind of see that happening at this picture down here. Then for the copper, there's copper ions in this solution. So in that blue solution, there's copper ions floating around. And what they're doing is they are picking up these 2 electrons that zinc is getting rid of, and they're becoming copper metal. So what you see here is you can see this blue color is starting to go away, and then you start to see this kind of rusty looking stuff forming on the metal strip. That's the copper metal. So this whole reaction is happening in this single beaker. What a voltaic cell does, or a galvanic cell does, is it takes this same reaction but you separate it into two different beakers. And when those electrons are transferred, those electrons are actually generating electricity, and you could then use those electrons to power some kind of external device. So these redox reactions have that potential to generate an electrical current. So an electrochemical cell carries out this generation of electricity from a redox reaction. So voltaic and galvanic cells, those are examples of electrochemical cells. Now the other one that we talked about that I said we'll talk about later is an electrolytic cell. An electrolytic cell actually uses electricity to drive a non-spontaneous reaction. So voltaic, galvanic, the ones we're going to start with, produces electrical current from a spontaneous reaction, whereas an electrolytic consumes current. So this would be, it requires external power or an external power source. And sometimes we would have time to do a lab in this, but usually we don't. But this is one, like if you do anything like an electroplating reaction, like if you plate one metal on the top of another type of metal, that's an electrolytic cell because you have to hook that up to some external power source. Whereas these voltaic cells and galvanic cells produce electricity spontaneously. So we're going to focus on these to start out with. Later on, we'll come back and we'll pick up the electrolytic. But both of those examples there are both considered electrochemical cells. So this is that same reaction that we did a second ago, but now it's happening in two separate beakers. So a couple differences to notice here. We still have zinc metal, and we still have a copper solution. So in this solution down here, just like we've talked about before, those nitrate ions don't really matter. They're like spectator ions. They're not going to change. Nothing's going to happen with those. They're just floating in solution. But what we do care about is we care about what's going on with the zinc and what's happening with the copper. So these are those reactions that I wrote on that previous slide. But now the zinc reaction is happening in this beaker. The copper reaction is happening in the other beaker. Okay, so when this is set up, notice now also that the metal that's in this beaker is not, or I'm sorry, it's still zinc, but now it's in a zinc solution because you don't want this reaction to happen inside the beaker. You want it to happen over this external circuit so that it generates that electricity, and then that electricity can be used to power a fan, a light, a buzzer, whatever it is that you have hooked up to that. Okay, so couple parts to this, and let me go to the next slide and then we might come back to this slide. So we'll talk through the parts, and then I put a little tiny version of this on this page so that we could kind of talk through it. So when you have one of these cells set up, the half cell is the half reactions. So one of the half reactions is happening in one beaker, the other one is happening in the other beaker. So the half cell is basically the beaker that's holding the two different reactions. The electrodes are some kind of metal through which the electrons can enter or leave the half cell. Now in this particular reaction, there's zinc metal in a zinc solution. And then over here we have copper metal in a copper solution, but it doesn't have to be that same metal in solution. And you'll see some examples of those later on. Sometimes they use like platinum electrodes because platinum doesn't tend to react with a lot of things, depending on what kind of a reaction is going on. The easiest ones have the metal in that metal solution. The anode is the electrode where oxidation is occurring. Okay, so this is where, like before, when we looked at this, the zinc was the anode, because the zinc was going from zinc metal to zinc plus two electrons. So this was losing electrons. So whichever side has oxidation, that's going to be your anode. Okay, so your mnemonic for that is anox. So if you remember anox, the anode is always where oxidation is happening. When you set these up, it's not always going to have the anode on the left, the cathode on the right. So which one of those beakers is the anode versus the cathode, it really doesn't matter. You could have them flipped. So that's why you always have to look at what's going on inside the beaker to figure out which is the anode, which is the cathode. Okay, so then the cathode is where you have reduction. So the cathode is over on this side. And that's where you have the copper ions in solution that are taking those electrons that zinc is giving up, and it's becoming copper metal or solid copper. Whereas up here I went from solid zinc to zinc ions. Okay, your mnemonic for that is red cat. So anox, red cat. Anox, oxidation, wherever the oxidation is, that's the anode. Wherever the reduction is, that's the cathode. Salt bridge is another piece that you have here. The salt bridge is this little piece in here, and in your notes you have a picture of this kind of off to the side that you can see. So the salt bridge has to be something that connects the two beakers. So if you think about a circuit, for a circuit to work, it has to be complete. You have to be able to go all the way around. So if the salt bridge wasn't there, the electrons would get to this side and then they wouldn't be able to make it back over to complete that circuit. Because if there's a break in the circuit, then that light is not going to light up or whatever it is that you have connected. So that salt bridge has an electrolyte in it. So electrolyte can be any salt solution. So in this case, I think this one has, let's see, nitrate and potassium. So it's some kind of, there's very sophisticated ones like this one where it's almost like a little glass tube. It can be as simple as soaking a piece of cotton string in a salt solution and laying that over the beaker. So it doesn't have to be a real complex thing. It just has to be something that has some kind of conductive substance. So a salt solution is the best thing to use for that, so that those electrons can then transfer through. So it neutralizes the charge buildup, and then, like we said, the most important thing is it completes the circuit. And when you look on there, what you can see, and I know this is kind of hard to tell on this little diagram here, but the electrons always travel from anode to cathode. So they always go, if you think in alphabetical order, that's kind of a way to remember it, anode to cathode. So the electrons go this way, and then as they move through, the negative ions of the salt bridge go to the left, because, well, depending on which direction they're going. So they go in the same direction as the electrons to complete the circuit. And then the positive ions in the salt bridge go in the opposite direction to balance it out. So in the salt bridge, the negative and positive ions are always going in the opposite direction. And if you follow the electrons around, then the negative ions are going to go in that same direction. There's another way that you can notate this, and some textbooks include this, some don't. It just kind of depends on how the author decides to add this in here. So I like to add this in here just so that you see another way to notate it. So there's something called cell diagram or line notation. What it does is it kind of gives you an overview of what's going on in that voltaic cell by using kind of a shorthand notation. So when you use this line notation, the oxidation half reaction goes on the left, reduction goes on the right. You use a single line, straight line going down as a phase barrier. If you have multiple species in the same phase, use a comma instead of a line, and we'll look at some of those later on. The double line represents the salt bridge, and then the general format is you go with the electrode, the electrolyte, and the electrode. So we're going to go to this next slide here, and that's going to give us a little better example of what's going on. Okay, so this is the one that we looked at before. So your electrode, so electrode again is the metal. So the metal piece that's stuck in each one of these solutions is your electrode. So in the left one, the electrode is the zinc. The electrolyte is what's in solution. So that's Zn+2. Remember, we don't care about the nitrate that's in that solution because those are just spectator ions. This represents my salt bridge. Okay, so that's what the salt bridge is. Then the electrolyte on the other side, which is copper, because there's copper in that solution. And then the electrode on the other side, which is solid copper. So it always goes, when you set that up, it always goes left to right. Electrode, electrolyte, salt bridge, electrolyte, electrode. And for these are pretty easy. You'll see some other ones that get a little weird where there's other stuff in there that's going on. This is going to be like your simplest format. So here's an example of a platinum electrode. So this is one, if I was gonna have you write one of these, it would be like the one that was on the previous page. I wouldn't make you do one like this because you can see there's some other stuff going on there. So on this one, your left side is pretty easy. So you've got solid metal, that's your electrode. Your electrolyte is what's in the solution, salt bridge with the double line. And then on this other side, you can see this is kind of a weird reaction going on here. So that's what that is. And then that one has a platinum electrode. Okay, and that's just a different version of an electrochemical cell. So we'll start with the easy ones and then we'll throw some of these in as we move forward. When you have a voltaic or a galvanic cell, you can do some calculations with this. So the main calculation that you're going to want to do with this is you're going to want to figure out how much electricity or how much current can you generate. So an amp is the flow of 1 coulomb, which is a measure of charge per second. So when we measure electrochemical cells, we're going to calculate or use amps. So an amp is a coulomb per second. That's what C divided by S means. And then 1 coulomb is that many electrons per second. And we're not going to right now focus on the electrons per second. We're more concerned with kind of a broader sense of what's going on. A couple other things we can measure is the potential difference. So this means every substance has its own potential difference associated with it. So basically, the potential to generate electricity, and different types of substances have different potential differences. So if you flip that page over that these notes are on, you'll see a chart there, and we'll talk about that chart next time, but that's your electrode potentials. So we'll come back to those when we come back to notes on Monday. So a volt is the unit for potential difference. So electromotive force is another name for a potential difference. They don't use that term as much, that EMF. So we're gonna call it potential difference or cell potential. But just know that sometimes you'll see that EMF thrown in there if you take other courses, or sometimes if you're looking in other places, sometimes they'll use that EMF. So cell potential is what we call the E cell. So this is the difference between those two electrodes. So the standard EMF is the potential difference under standard conditions. So just like in the last chapter where we had standard conditions for G and H, there's also standard conditions for E cell or cell potential, and we'll talk about those as we move forward.